Welcome to this deep dive into one of the most fascinating topics in nanoscale engineering, strain-engineered nanomembranes and impossible curvatures. Today we're going to explore how ultrathin films can spontaneously roll up, wrinkle, and form three-dimensional microstructures, with curvatures that seem to defy the laws of classical mechanics. Let me start with a fundamental question. How can materials that are only a few nanometers thick bend into radii of curvature that would be impossible for thicker materials? According to classical plate theory, when you try to bend a material too sharply, it should crack or buckle catastrophically. Yet we observe nanomembranes rolling up into tight tubes without breaking. The answer lies in the unique physics of the nanoscale regime, where stored elastic energy and quantum mechanical effects allow behaviors that are forbidden at larger scales. First, let's define what we mean by nanomembranes. These are ultrathin films of material, typically between 1 and 100 nanometers thick. To put this in perspective, these films are thinner than most viruses. 100 nanometers is about 1,000th the width of a human hair. Nanomembranes can be made from semiconductors like silicon or gallium arsenide, metals, oxides, or complex multi-layer stacks of different materials. Here's a schematic showing the extreme difference in scale. The nanomembrane on top is incredibly thin compared to the bulk substrate below it. Now let's talk about where the strain comes from. There are three primary mechanisms that create built-in stress in these nanomembranes. The first mechanism is lattice mismatch. This occurs when you grow one crystalline material on top of another with a different atomic spacing. Every crystalline material has a characteristic lattice constant, which is the distance between atoms in its crystal structure. Here we see two different materials with different lattice constants. The top layer has atoms spaced further apart than the bottom layer. When you grow layer A on top of layer B epitaxially, the atoms in layer A are forced to stretch or compress to match the substrate's lattice constant. This creates enormous built-in stress. The strain is defined as the difference in lattice constants divided by the film's natural lattice constant. Even a 1% mismatch creates huge stresses. A classic example is silicon-germanium bilayers. Silicon and germanium have about a 4% lattice mismatch, creating substantial strain when layered together. The second mechanism is differential thermal expansion. Different materials expand and contract at different rates when temperature changes. Many thin film deposition processes occur at elevated temperatures, sometimes hundreds of degrees Celsius. When the sample cools down to room temperature, materials with different thermal expansion coefficients will try to shrink by different amounts. Since they're bonded together, this creates stress. Here's a visualization. Upon cooling, the top material wants to shrink more than the bottom material, but they're bonded together. This creates compressive stress in the top layer and tensile stress in the bottom layer. The third mechanism is deposition-induced stress. The process of depositing atoms onto a surface can itself create intrinsic stress. Techniques like sputtering, evaporation, and chemical vapor deposition often create films with built-in stress, even without lattice mismatch or temperature changes. The energy of incoming atoms, the surface mobility, and the deposition rate all influence whether the resulting film is in tension or compression. All of these mechanisms create stored elastic energy in the film. This energy is like a compressed spring, waiting to be released. The stored elastic energy scales with Young's modulus Y, the square of the strain epsilon, and the volume of the strain material. Because strain can be several percent in these systems, the energy density can be enormous, sometimes reaching gigapascals of stored stress. Now here's where it gets really interesting. How does this stored energy get released? If you selectively etch away the substrate and release the strain nanomembrane, it can relax the stored stress by bending. This is energetically favorable. Step 1. We have a strained film sitting on a substrate. The substrate constrains the film and prevents it from relaxing. Step 2. Once released, the film spontaneously rolls up. The top surface in compression and the bottom surface in tension naturally create curvature. The radius of curvature that forms depends on how the strain varies through the thickness of the film. A linear strain gradient produces uniform bending. The curvature, which is 1 over the radius r, equals 6 times the strain difference delta epsilon divided by the film thickness h. Now let's address why classical plate theory fails in this regime. This is a crucial point. Classical plate theory was developed for macroscopic plates where the deflection is small compared to the thickness, and the thickness is small compared to lateral dimensions. In classical theory, the bending stiffness scales as Young's modulus times the thickness cubed. This means thicker plates are much harder to bend. The bending rigidity, d, equals Young's modulus E times thickness h cubed, divided by 12 times 1 minus Poisson's ratio nu squared. Let me ask, why does this break down at the nanoscale? The answer involves several factors. First, when thickness becomes a few nanometers, the bending energy becomes incredibly small because of that cubic dependence on thickness. Meanwhile, the strain energy remains large. Second, surface effects become dominant. At the nanoscale, surface energy and surface stress can be comparable to bulk elastic energy. Classical theory ignores these surface contributions. Third, the discrete atomic structure matters. When you're only 10 or 20 atoms thick, you can't treat the material as a continuous medium. Quantum mechanical effects and atomic scale rearrangements become important. This brings us to the concept of impossible curvatures. What do we mean by this term? We're talking about curvatures where the radius of curvature is smaller than the thickness of the material it's. This would be impossible for thicker materials. Mathematically, we're in a regime where r is less than h. For a macroscopic sheet of paper, this would mean rolling it into a cylinder narrower than the paper's thickness, which can't be done without crumpling. Compare a thick film on the left, which can only bend gently, to a nanomembrane on the right that can roll into an incredibly tight radius, much smaller than its own thickness. Experimentally, strain-engineered nanomembranes have been observed rolling up into tubes with radii as small as 10 to 50 nanometers, starting from films only 5 to 20 nanometers thick. One of the most exciting aspects of this phenomenon is the spontaneous self-assembly into three-dimensional architectures. By engineering the spatial distribution of strain across a nanomembrane, you can program it to fold into a specific three-dimensional shape when released. A uniform bilayer with top-bottom strain asymmetry will roll up into a microtube, like a miniature scroll. Here's a cross-sectional view of a rolled-up microtube. The nanomembrane wraps around itself, creating a hollow cylindrical structure. More complex strain patterns can create wrinkles, waves, or origami-like folds. You can make helical ribbons, folded boxes, or even saddle-shaped structures. Let me give you a concrete example. Silicon-germanium microtubes are one of the most well-studied systems. First, a thin silicon-germanium alloy layer is grown epitaxially on a silicon substrate. The lattice mismatch creates compressive strain in the silicon-germanium layer. Then, a sacrificial layer underneath is selectively etched away. This releases the strained silicon-germanium film. Upon release, the film spontaneously rolls up into a tube. Depending on the layer thickness and composition, the diameter can be anywhere from 5 to 50 micrometers. This diagram shows the rolling process. The flat strain membrane on the left spontaneously transforms into the tightly rolled tube on the right. Interestingly, these tubes often have multiple windings, like a jelly roll or Swiss roll cake. The number of turns depends on the initial lateral dimension of the film. Now let's discuss applications. These strain program structures have enormous potential in various fields. First, compact electronic devices. By rolling up semiconductor nanomembranes, you can create three-dimensional device architectures in a very small footprint. For example, rolled-up capacitors can achieve extremely high capacitance density because the effective area is multiplied by the number of windings. Second, strain-tunable photonic devices. The optical properties of semiconductors are very sensitive to strain. By applying controlled strain, you can tune the band gap of the semiconductor, changing the wavelength of light it emits or absorbs. Rolled-up tubes can act as optical microcavities or ring resonators. Light can be confined and circulated within the curved geometry, enabling compact lasers and filters. Here's a schematic of an optical microcavity formed by a rolled-up tube. Light propagates in a circular path, indicated by the yellow arrows, creating resonant modes. Third, flexible sensors. Nanomembranes are inherently flexible and can conform to curved surfaces. These sensors can wrap around blood vessels, nerves, or other biological structures for in vivo monitoring. The curvature and strain in the membrane directly affect its electrical resistance, providing a sensitive readout mechanism. Fourth, three-dimensional micro and nanorobotics. This is perhaps the most futuristic application. Strain-programmed self-folding can create actuators, grippers, and other robotic components at the microscale. Imagine tiny robots that start as flat, lithographically patterned sheets and then fold themselves into functional three-dimensional machines when triggered by chemical or thermal stimuli. This illustration shows a flat precursor on the left that self-folds into a gripper structure on the right. The yellow lines represent hinges created by strain patterns. The release and folding can be triggered by various stimuli such as temperature changes, pH changes, or light exposure, enabling remote control. Let me now provide some mathematical insight into how we model these systems. The total energy of the system includes the elastic strain energy stored in the film and the bending energy required to curve it. Total energy equals strain energy plus bending energy. The bending energy is the integral over the area of 1/2 times the bending rigidity d times the curvature kappa squared. The system spontaneously adopts the configuration that minimizes the total energy. This is a balance between relieving strain and the cost of bending. For a simple bilayer with a strain difference between the two layers, we can derive an equilibrium radius. The radius r equals the thickness h divided by 6 times the strain difference delta epsilon. Notice that smaller strain differences give larger radii, and vice versa. This simple formula only works when the thickness is uniform and the strain gradient is constant. More complex geometries require numerical simulation. Let's touch on some advanced topics. Gradient strain engineering allows even more control over the final shape. By varying the composition or thickness laterally across the membrane, you can create non-uniform strain distributions. This leads to complex three-dimensional shapes upon release. You can program saddle shapes, helices, or other Gaussian curvature geometries. A graded composition, shown at the top, creates non-uniform strain. Upon release, this results in asymmetric rolling, as shown at the bottom. Let me pose a question. What limits the minimum radius of curvature we can achieve? The answer is, ultimately, fracture stress sets a limit. If the strain becomes too large, the material will crack. Additionally, at radii comparable to interatomic spacing, the continuum approximation breaks down completely. For semiconductor nanomembranes, typical minimum radii are around 5 to 10 nanometers before fracture or structural instability occurs. Another interesting question. Can we reverse the process and unroll the tubes? Yes, in some cases. Applying mechanical force or temperature cycling can cause the tubes to unroll. This reversibility is useful for reconfigurable devices. Let's briefly discuss fabrication techniques. How do we actually make these strain-engineered nanomembranes? For semiconductors, molecular beam epitaxy, or metal organic chemical vapor deposition, are used to grow atomically precise strained layers. Selective wet or dry etching removes a sacrificial layer underneath, releasing the strained membrane. Transfer printing techniques can pick up these membranes and place them onto flexible or curved substrates for device integration. Step 1. You start with a layered structure, the strained layer on top, a sacrificial layer in the middle, and the substrate at the bottom. Step 2. Selective etching removes the sacrificial layer. The green arrows indicate the etchant attacking the sacrificial material. Step 3. The released membrane spontaneously rolls up due to the strain gradient, forming the final tubular structure. Like any emerging technology, strain-engineered nanomembranes face several challenges. First, achieving precise control over the spatial distribution of strain remains difficult. Small variations in composition or thickness can lead to unpredictable shapes. Second, integrating these three-dimensional structures with existing planar semiconductor technology is non-trivial. Most electronics fabrication is based on flat substrates. Third, scaling up to production while maintaining reproducibility is challenging. Each structure is somewhat unique due to stochastic factors in the release process. Looking forward, researchers are developing programmable shape-memory nanomembranes that can switch between multiple configurations on demand. Bio-inspired designs that mimic plant movement or natural origami patterns offer new possibilities for soft robotics and adaptive structures. Let me give you an analogy to help understand this phenomenon. Think about a bimetallic strip, like in an old thermostat. A bimetallic strip consists of two different metals bonded together, each with a different thermal expansion coefficient. At room temperature, the strip is flat. Both metals are bonded together and in equilibrium. When heated, the metal with higher expansion coefficient expands more. Since they're bonded, this creates curvature. The strip bends toward the side with lower expansion. Strain-engineered nanomembranes work on the same principle, but instead of thermal expansion, they use built-in lattice mismatch or deposition stress. The effect is permanent unless you actively change the strain. Let me work through a quantitative example to make this concrete. Consider a 20 nanometer thick silicon germanium bilayer with a 2% strain difference between the top and bottom. Using our formula, the radius equals thickness divided by 6 times strain difference. That's 20 nanometers divided by 6 times 0.02. 20 divided by 0.12 equals about 167 nanometers. So this membrane will roll up into a tube with a radius of roughly 167 nanometers. The diameter is about 334 nanometers. For comparison, a red blood cell is about 7,000 nanometers in diameter. So this tube is incredibly small. If we increase the strain difference to 4%, the radius drops to 83 nanometers, double the strain, half the radius. This linear relationship gives us precise control. What do we actually see in experiments? Let me describe some key observations. The rolling process is extremely fast. Once the sacrificial layer is etched and the membrane is released, it rolls up within milliseconds. The resulting tubes can be several millimeters long, but the wall thickness remains just a few nanometers. This extreme aspect ratio is unique to nanomembranes. Multiple concentric windings are common, creating a spiral or jelly roll structure. The number of turns depends on the initial width of the released area. This cross-sectional view shows multiple windings. Each dot represents a layer of the nanomembrane wrapped around it. At these extreme dimensions, surface effects and quantum confinement become important. In a 20 nanometer thick film, surface atoms can represent 10 to 20% of the total atoms. Their properties differ from bulk atoms. Surface stress, which is the force per unit length along the surface, can contribute significantly to the total stress in the membrane. In very thin semiconductor membranes, quantum confinement perpendicular to the film changes the electronic band structure, affecting optical and electrical properties. How does strain engineering compare with other self-assembly methods? DNA origami is a powerful bottom-up method, but is generally limited to structures smaller than a few hundred nanometers. Self-assembled monolayers create highly ordered 2D structures, but don't easily extend to 3 dimensions. Strain engineering uniquely bridges the nano to microscale, creating structures from tens of nanometers to tens of micrometers. It combines top-down lithography to pattern the initial strain distribution with bottom-up self-assembly to form the final 3-dimensional structure. Let me close with some final thoughts on why this field is so exciting. Strain engineering represents a paradigm shift in how we think about micro and nanofabrication. Instead of building structures layer by layer, we encode the final shape in the material's stress state. It's a form of mechanical programming where strain is the code and the 3-dimensional structure is the output. The physics is incredibly rich. Elasticity theory, surface science, and quantum mechanics all interplay at these scales. The applications span an enormous range, from implantable medical sensors to quantum computing devices to microscale robotics. Let me summarize the key takeaways from this lesson. First, built-in strain from lattice mismatch, thermal expansion differences, or deposition stress creates enormous stored elastic energy in nanomembranes. Second, releasing these membranes allows them to spontaneously bend into curvatures that would be impossible for thicker materials. Third, classical plate theory breaks down at the nanoscale, where surface effects and discrete atomic structure dominate. Fourth, by engineering the spatial distribution of strain, we can program the final 3-dimensional shape with remarkable precision. Finally, the applications are vast and include strain-tunable electronics and photonics, flexible sensors, and three-dimensional micro and nanorobotics. The field of strain-engineered nanomembranes is still in its early stages, but it holds immense promise. We're learning to read and write in the language of mechanical stress at the nanoscale, opening new dimensions for materials design. The next decade will likely see commercial devices based on these principles, from medical implants to quantum sensors. Thank you for joining this deep exploration of strain-engineered nanomembranes and impossible curvatures. This is truly a frontier, where physics, materials, science, and engineering converge to create entirely new possibilities.